couple things to note is that there are these charts that I believe we're not using in our examples today, but you may need in the practice. They're on pages 494 and 498. They're just in that section of the textbook. So they have things like, actually we kind of do need them, except maybe I've got it already written out. So the decibels of an average rock concert, that's obviously average, different concerts would be different, but is 120. A normal conversation is 60 and so forth. Okay, and so you might need this chart as a reference to find those numbers. The question will say, compare the intensity of the loudness of a subway to a space shuttle launch or something like that. And you'll need to look those up. And then there's a pH scale. There might be another one in there as well. There's a pH scale as well, so you can refer to those. We may use them on the test. If we use them on the test, I'll give them to you. You don't need to memorize these. Okay? Okay. I'm going to take a look at an example here. You've all heard of the decibel scale or the decibel unit. Am I correct? You know what a decibel is? And you've seen sometimes, like a home stereo as you're scrolling up and down on the volume. Mine actually just is like volume like 1, 2, 3, 4, 5. But some of them list the decibel, right? And or on a computer sometimes if you go into the options, it'll show you the decibel level of the volume, right? So we've all kind of seen it or understand what it is in some situations. What you probably don't know is that the decibel scale is logarithmic. So in fact, so again, you don't need to know how to draw a logarithmic scale. But my point here is if you go back to that chart, I know you're writing this down, but hopefully you can kind of listen to what I'm saying as well. If you go back to that chart, and it was kind of counting like by tens or whatever, right? Like, but it wasn't equal. But it was like 30 and then 60, 70, 80, 90 or whatever it was. That's not a linear scale. So an increase of 10 from one to the next and another increase of 10 from one to the next isn't the same increase in intensity. Does that make any sense to you? Let me go back and just give you one little example here. A soft whisper to a normal conversation looks like the intensity is doubling. And then from a normal conversation to a rock concert would be another double. But that's not the way it works because the scale is not linear. Just like those graphs that we were looking at. Okay? So we're going to compare the intensities of the two sounds. Normal conversation that has a loudness of 60 decibels. That was from the chart, right? But it's written down here. And a rock concert with 120. Now, we did a couple of questions throughout this unit. I remember an earthquake question where you were given the values, you just had to plug them in and rearrange, that kind of thing. So there's a little bit of that here. You could get a question like that as well. Okay? But what this question is asking us to compare the two intensities is a little bit different. Okay, so let's start with a rock concert. So the loudness, which in our equation is that capital L, is 120. And then our equation is given up there. It's L equals 10 log. That's a capital I over IO. And IO is a constant, or I0. The lowest intensity that can be heard by humans. Okay, so 120 goes in for L. Whoop, yeah, 120 goes in for L equals 10 log of I over I-O. Is everybody good? A lot of these are going to kind of work out the same way or in a very similar way. So the first thing I'm going to do is divide both sides by 10 because why not? So I get 12 divided, or 120 divided by 10 gives me 12. Then I'm just going to rewrite this in exponential form. So what's the base? It's log base 10, right? Because it's not written. So 10 to the 12 is equal to I over I0. Everybody okay with that? And then I'm going to multiply by I0, so I get this solved for, whoops, times I0 equals I, and I'm going to add, I should have had it all the way, but a little R for rock concert. So that's the intensity of a rock concert is 10 to the 12 times I0. Which is a constant. We don't have to worry about it right now. Is that okay? Okay, do the same thing for a conversation. Just follow the same steps. Go ahead. Get that okay? So I got 10 to the 6 times I0. Okay? Is the intensity of a conversation. So now if we compare these two, that's going to be the intensity of a rock concert, and I'm going to divide it by the intensity of a conversation. It gives me 10 to the 12 times I0 over 10 to the 6 times I0. So that's a constant that cancels out in this case. And this is what's interesting. Math was pretty simple. The 12 on top obviously came from the 120 decibels. 6 on the bottom came from the 60 decibels. And again, like I said, that is double from the graph, or from the chart, sorry, right? 120 is double 60, and the exponent is double. But when you double the exponent, you're not doubling the number, right? You're doubling the exponent. That's a different thing. So it's not twice as loud or twice as intense. This is what we mean by it's not a linear scale, it's a logarithmic scale. Okay, so 10 to the 12 divided by 10 to the 6 is 10 to the 12 minus 6, which is 10 to the 6, which is 1,000,000. Therefore, a rock concert is 1 million times more intense. The decibel scale was twice, but the intensity is actually 1 million times more. Interesting. Okay, so, and you can see how powerful it is. There's a lot of things in the world that are logarithmic. You've probably heard, I remember hearing this like when I was a kid and not really understanding what it meant. I got it, but I didn't understand exactly why or what was going on. But that earthquakes, which we already looked at, are the same way, right? So an earthquake that's 4 on the Richter scale, and an earthquake that's 5, and then an earthquake that's 6, it's not the same increase. The increase from 4 to 5 is not huge, but 5 to 6 is getting big. And 4 to 8 isn't like twice. It's like way, 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 way more intense, right? Earthquakes that are 7 and bigger, up to 8, are like really intense, right? Those are huge, huge earthquakes. And as you go further up that scale, you don't see earthquakes that are in the 9s and 10s. I don't know if that's ever happened. But that's getting so large because the scale isn't linear. We make it linear. Like we turn it into a linear for our own ease of understanding to make the numbers nice. So the Richter numbers are linear, just like the decibel numbers are linear, but the actual comparison isn't. It's logarithmic. Very interesting. Okay, let's do one more, which is about earthquakes. There was a very famous earthquake in Haiti in 2010. Do you remember when that happened? Caused a lot of destruction. There's still, Haiti is a difficult country, has a lot of instability. And the earthquake didn't help. So it measured a 7.0 on the Richter scale. But the same year, there was an earthquake in Chile that measured 8.8. And you may have heard of it, I don't know, but probably not. It certainly was not as well known. It probably made the news, but everybody knows about the earthquake in Haiti. Everybody knows about the, what's the name? The big flood that happened, what was that, in like the early 2000s, or 2005 maybe, or something like that. There was a big tidal wave, right? But some of these other ones, we don't hear about. Anyway, so let's take a look at this. So I'll get you started, and then I want you to go through the rest of this one. So, here's our formula. If you remember, well, I'm sure we don't remember it, but we've seen this. We used it. So for the Richter scale, it's log of A over T, where A is the amplitude plus B. B is a constant, and for us, T is going to be a constant as well. Okay, so we have to do Chile and we have to do Haiti. And Chile was 8.8 equals. And Haiti is 7.0 equals. Okay, so go ahead and try to rearrange. This one's a little bit different. The other one had a times 10. We were multiplying. This one's a bit different, but otherwise pretty similar. So you're solving for A. Sorry, if that wasn't clear, you're solving for A. Because the other two are constants for us. Okay, looks good. Most people are on the right track. Take a quick look. I subtracted B. You got to do that first, and then rearrange. So this whole, the left side of the equation, the whole thing becomes the exponent. So it's again the base of the log, which is base 10. 10 to the 8.8 minus B, right? That minus B is in the exponent. Equals A over T, and then bring the T over just like we did in the last one, equals A, and I called that AC for Chile. Okay, and then continue with Haiti. So I got T times 10 to the 7 minus B is the amplitude in Haiti. The amplitude in Chile was T times 10 to the 8.8 minus B. Is that good? Okay, so now let's compare. Nope. Okay, what do I do first? This one's, again, a little bit different. It's pretty straightforward, though. What do we want to do first? Vivian?
Cancel out the T.
Good. Like I said, the T is the same for both. Now what can I do? Tom?
Didn't bring down the exponent with make it like in those logs or whatever.
I could rewrite it in logs, but I don't know that that's necessarily going to help us. It might just kind of undo what we already did. What else do you think, Sam? Okay, nice. So 10 to the 8, just let's rewrite it the nice long way, minus the exponent on the bottom. That's what we did in the last one, but we didn't show it, right? It was 10 to the 12 over 10 to the 6. Subtract the exponents, 12 minus 6 is 6. But in this case, I'm subtracting something that is an expression, so I have to subtract the entire thing. Just be careful of that. And negative b minus negative b is negative b plus b. So those guys are gone. And I end up with 10 to the 8.8 minus 7, which is 10 to the 1.8. Ten to the 1.8. Ten squared is 100, so it's less than that. So it's 63.096. Therefore, the earthquake in Chile was about 63 times more intense. That's huge. But different countries have different infrastructure and are impacted by these things in different ways, right? Maybe Chile's more used to earthquakes, I don't know. Okay. Any questions? Page 499, 1 to 8, and 10.